Hi, I am Renan from UIUC, presenting our work Making Visual Transformers Truly Shift-Equivariant. This is a joint work with Teck-Yian, Minh, and Raymond. For semantic segmentation, given an input x, f theta generates an output containing predicted mask labels. Ideally, if a shifted version of the input is passed to f, its output should correspond to a shifted version of the original prediction. This is known as shift-equivariance and is a desirable property of semantic segmentation models. Similarly, for classification, given an input image, its class is predicted by a function f. Ideally, shifting the input shouldn't change the prediction, since the image depicts the same object. This is known as shift-invariance. Despite the use of convolutional layers, known to be shift-equivariant, recent work has shown these models do not preserve such property. In fact, small input shifts affect their predictions even when using anti-aliasing layers. In this work, we focus on vision transformers and their shift consistency. Given its design principle of extracting patches, recent work has shown they are sensitive to input shifts. Given an object and its shifted version, patches are selected in a fixed manner. So, extracted patches are different even under small offsets, generating different representations and stable predictions. This can be explained by exploring BIT components. For example, the swing uses tokenization, window-based self-attention, and patch merging, among other layers, to extract tokens. These are then averaged across space and passed to a fully connected layer to generate logits. If the feature extraction step is shift-equivariant, then the global average pooling makes the model shift-invariant. However, this is not the case since several modules such as patch tokenization and merging, window-based self-attention, and relative position embedding break shift-equivariance. Take as example the tokenizer. Given an input and its shifted version, patches are selected independently of input properties, so different patches are obtained even for small shifts. So, subsequent BIT layers operate on distinct tokens despite small input shifts. So, how can we design shift-equivariant vision transformers? Specifically, we are interested in obtaining circular shift equivariance by construction. Similar to working CNNs, the circular shift assumption is adopted to deal with the loss of information at the image edges. We also want our models to improve shift consistency under standard shifts to make them useful in practice. We also aim for a general design and focus on hierarchical BITs based on their state-of-the-art performance. And finally, we want our models to be end-to-end trainable. We propose redesigning the BIT modules that break shift equivariance in a data-adaptive manner. First, we introduce an adaptive tokenization that selects patches based on input properties. Given an input and its shifted version, we compute all possible patch partitions and subsequent tokens in an efficient manner. Then we compute the response of each token to a shift-invariant selection criterion F, and select the partition with the highest response. Given its shift-invariant property, partitions with the highest response to F are guaranteed to be the same up to a shift, leading to shift equivariance. Next, we propose an adaptive window-based self-attention module. We align the input tokens using a shift-invariant selection criterion to choose windows in a consistent manner. In the original implementation, given a token representation and its circularly shifted version, windows are selected under a fixed grid. So, local self-attention is applied within different windows, generating different output tokens and breaking shift equivariance. In contrast, given an input token representation, our approach considers all its possible window partitions and compute their average window energy. This leads to an energy vector for each possible partition. Next, using a shift-invariant selection criterion denoted as G, we select the partition with the highest response. Given a shifted token representation, notice that the window partitions and the energy vectors are shifted versions of the original ones, so selecting a window partition that maximizes the response to G guarantees the same window partitions up to a circular shift. Following this, given an input token representation and its shifted version, we align the tokens prior to computing the window-based self-attention. This ensures windows composed by the same tokens and thus a shift-equivariant output representation. To encode token positions in a circularly shift-consistent manner, our data-adaptive position embedding uses a circular relative distance matrix. While original relative position embeddings rely on a linear distance between tokens, such a distance doesn't match the circular shift assumption of interest. In contrast, our proposed positional embedding takes into account a circular relationship between tokens, preserving perfect shift consistency. We run image classification experiments on CIFAR and ImageNet datasets under circular shifts, attaining significant accuracy improvements and perfect shift consistency across BIT architectures. We extend our experiments to standard shifts, where we show that, despite not satisfying our data assumptions, our models get improved or on par accuracy while boosting shift consistency. Under circular shifts, our adaptive VITs generate stable representations across the pipeline, in contrast to default models where deviations occur due to input shifts. Note that such robustness is obtained by design without any refined data augmentation. For semantic segmentation, we apply the same design principle to the operated model, leading to an end-to-end circularly shift-equivariant segmenter. Tested under circular and standard shifts, our models improve segmentation accuracy and shift consistency by a large margin. As illustrated, they lead to more stable segmentation masks. To conclude, we propose a data-adaptive framework to design shift-equivariant vision transformers. Our models are perfectly shift-equivariant under circular shifts, which is achieved by redesigning all the VIT modules that break shift equivariance. Our method boosts shift consistency and obtains competitive accuracy on image classification across different VIT architectures, both under circular and standard shifts. We also obtain improved shift consistency on semantic segmentation by using the same design principle, while improving segmentation accuracy without increasing the model capacity nor additional data augmentation. For more details, please check our project website. Thank you.